Okay, thanks to the organizer for the kind opportunity. And yeah, this is a joint work with Jonas Azzam and Mihalis Mougoglou. Okay, so I'll start very basic with the Rademacher theorem. So we take f to be a Lipschitz function, then f is differentiable almost everywhere. This is Rademacher theorem. And let me mention in passing that will become relevant later that Rademacher theorem still holds when so f is defined on a rectifiable set E. But then, so going back simply to the Euclidean case, what this means is that almost everywhere, if I look around the point of my function and I zoom in, then instead of this asymptotic sense, in the limit, my function will look like an affine function, so that the graph will look like a plane or a line. And okay, this is all good. So then suppose now we define this quantity, so f from Rd to R, then A, an affine function. Then we define this omega f of x r with A as this sort of average integral where we compare f to A, and then we divide by R because we want a quantity scale invariant quantity. And when we define omega f to be the sort of infimum of this quantity over all affine maps. So what this does is to check at each scalar location, how far is my function from being affine? And I mean, we've seen many times in this workshop, the beta numbers, and these omega numbers are like functional versions of these beta numbers. Then what Rademacher theorem says is that this omega quantity will go to 0 as we zoom in, so as R goes to 0. So this gives us this asymptotic information. Okay, in the limit, we know that this omega will be small. But is this a whole story? Like Rademacher theorem doesn't say anything about any given definite scale. So at scales 1/1000, it doesn't say anything. 1/1,000,000,000 doesn't say anything. So sort of put into focus the problem, let us consider this silly example. So if delta is some positive small constant, then we define f of delta in this way. So it's delta times sine x divided by delta. And let us see if this function, how many bad scales does it have, in the sense that the omega number is large. So if the scale is large, much larger than delta, then my function will be very small. And so then if we take the affine approximating map to be equal to 0 everywhere, then this will be a good approximation. So my omega number will be small. If R is comparable to delta, then we will have these oscillations. And then, of course, my omega number will be large. Then again, when we go below this, and R is very small, much smaller than delta, then the smoothness of sine kicks in. And so omega, we can approximate omega, sorry, we can approximate f by an affine function, then omega will be small. So what this silly example says is that really this f of delta has just one bad scale. Okay, and of course we cannot expect this to be generally true for a Lipschitz function, because there's enough if we can take a sum of this f of delta for different delta, we have as many scales, as many bad scales. But the following is true. So if epsilon is some positive number, and then we define bad epsilon at x to be the set of integers, so that these integers j, so that omega f at x and 2 to the minus j is large. Okay, so these are all the scales where like my omega is large. Then we have these estimates on the cardinality of the bad scales. Okay, and so this integral, the number of bad scales, is controlled by the Lipschitz constant. So this is saying, in fact, not, of course, this is not that we just have one bad scales, but the number of bad scales is very much controlled. And so there is much more information here than in Rademacher theorem. And this is a consequence of the following theorem, which I'm now going to describe. So if we define this square function, we saw many square functions in this workshop, this is just another one, which is this Dini integral of this omega quantity we defined before. Then we have this theorem, which is by Dorronsoro in the 86. And it says that if we take P between 1 and infinity and F in LP, then in fact, we have this quantitative estimate that the LP norm of the square function is comparable to the LP norm of the gradient of the function. Okay, and in particular, if F is in the Sobolev space 1P, if W1P, if and only if the LP norm of the square function is finite. Okay, so and then from this theorem, one can sort of localize and use and take a Lipschitz function and show that this measure here is a Carlson measure. We saw many Carlson measures in this workshop again. And he is saying that essentially for Lipschitz function, this quantity is small in most spaces and most scales. And from this Carlson measure estimate, we get the bad scale estimate we saw before. Okay, so in this sense, Dorronsoro theorem is a quantitative version of Rademacher's theorem. Okay, so this is it. And now I mentioned in passing, Rademacher theorem holds for function defined on rectifiable sets. So then it's natural to ask, is it true about this quantitative version of Rademacher theorem? Does it hold on rectifiable sets? And the main result I wanted to present is this joint work with Jonas and Mihalis, and is that yes, on uniformly rectifiable set. Okay, so if E is a subset of Rn, which is the uniform rectifiable, and we saw uniform rectifiable set many times, and I just remind you that it is a quantitative version of rectifiability. Then if P between 1 and infinity, we have the following two statements. So let's take and say, yeah, we'll read the theorem and then make remarks about some objects that we appear that they're not clear what they are. So if one says that if F is a function from E to R, as in the Sobolev space, then we have one inequality of Dorronsoro theorem. So the square function is controlled by the gradient. And then on the other hand, if we start from F to be Lipschitz on E, then we have this other inequality of Dorronsoro theorem. Okay, so the two together give a Dorronsoro theorem. And I remark that both in 1 and 2, the square function is somehow similar to Dorronsoro square function, so with this omega quantity, but is also a bit different, and we'll see later. And okay, let me remark that something similar was proven by David and Sam only for Lipschitz function, in the sense that this quantity is with sigma, that is the Hausdorff measure, C to our set, is a Carlson measure. But of course, this is more general. Okay, but so there are lots of things that appeared here that I haven't defined. So let us go through them and see what they are. Okay, so the inverse theorem, the first thing that appears that is not obvious what it is this M1P Sobolev space. So what is this? So this is the high-wash Sobolev space, which is defined as follow. So a function is in this space if it's LP function. And moreover, we can find another LP function, which will be called the high-wash upper gradient, such that this inequality holds almost everywhere, okay? And so if we were in the Euclidean plane and F was nice, this inequality would hold with G to be the sort of norm of the gradient of F, okay? So this is a sort of generalization of Sobolev function, and it was introduced to study Sobolev space on matrix space, where you don't have a notion of gradient, a traditional notion. And yes, this gradient HP will be the minimal high-wash upper gradient. Okay, so far so good, but then, so one can ask, okay, why do you bother with this strange Sobolev space? Why couldn't we just use the tangential gradient, which is more natural, perhaps? And the answer is simply that this inequality is false in the generally we work on UR set if here we have the tangential gradient. And so why is this? So suppose we take these two eggs and we join them and they're epsilon apart, okay? And we join them by a tiny tube which has diameter epsilon. And okay, so then our E will be the surface of this object. And of course, this is a uniform rectifiable set. And then we define f, the function on the surface, to be equal to 1 here, to be equal to 0 here, and to move from 1 to 0 smoothly along the little tube, okay? Then f is Lipschitz, depending on epsilon, but it doesn't matter. But then one can compute that the square function that we have is much larger in this case than the norm of the tangential gradient, okay? And this is essentially why the reason why is that because like the gradient is only positive in this little tube. This little tube has so little surface area that this doesn't pick up the thing. Then if we consider this other example where now instead of having one little tube, we put lots of little tubes so that we fill in a proper way the space, then this won't be a counterexample to this inequality with the tangential gradient, because essentially this space supports a Poincare inequality with respect to the tangential gradient, and this space doesn't. Okay, and so this says like, so in this case, this is a uniform rectifiable set. We cannot hope for a theorem like this in this generality. And so then this is the reason why we use the Hausdorff space, because the nice thing about them is that any function in the Hausdorff space satisfy a Poincare inequality with respect to its high-wash upper gradient, regardless of the space. So in a sense, if we go back here, a function in the Hausdorff space will build itself its little bridge, in a sense, and so it will satisfy Poincare inequality. And of course, one can see that what makes the existence of a Poincare inequality, the fact that a Poincare inequality, there is a Poincare inequality on a space, makes this inequality plausible, is because on the left-hand side here we have something that looks vaguely like our coefficient omega. Okay, so that's roughly the reason. And so this is sort of to give some motivation why we used this Sobolev space in our statement. Okay, so now next remark is I mentioned that we use new coefficients, this gamma f, which I haven't defined yet. And one, of course, can ask why didn't we just use this omega, the original Dorronsoro coefficient? And the reason, and again, theorem 2 in this case would be false with this omega simply. So if we consider, for example, an example, like, so we take G to be some smooth function, like in this case, and this is the graph of G, okay? And then we define F to be an affine function on this surface. And then one can check that it may happen that the gradient, the tangential gradient, has L2 norm positive, while of course the omega number will be 0. And so the sort of main reason behind this is that we need a coefficient that sees the geometry of the surface we are on. Because if before we were in Euclidean space, there was no geometry, everything was flat. Now things are curved, so we need our coefficient to see this sort of curvature. And so that's why we define this gamma to be the omega number, because of course you won't check how well a function is affine approximated. And but we add a term which sees the geometry. So here you see that the beta numbers appear that we so many times, and it's sort of what sort of sees the geometry of the thing. In fact, the sort of theorem holds for where here we put different coefficient, like for example, it also has alpha number, but for the sake of presentation, this will be enough. Okay, so these are the remarks I wanted to mention. And okay, so then now some applications. So if one takes a UR set and assumes a priori as well that it supports a Poincare inequality, then by a lemma in a paper by Mihalis and Xavi, the high wash point, the LP norm of the high wash gradient and the LP norm of the tangential gradient is actually comparable. Yeah. Okay, this is where I learned it. Yes. Okay, probably okay. Possibly it was already known, but okay. And so then we really have a sort of full nice comparability like in the original Dorronsoro. And also a nice, which I won't go into details here, but a nice application is that we can construct an extension of Sobolev functions on the uniform rectifiable boundary of corkscrew domain. So in other words, you can phrase this as we construct a trace map from a certain space, a nice space in the domain of function with the non-tangential maximal function. Non-tangential maximal function of the gradient of function in U and some conical square function to a space, to the Sobolev space on the boundary. And this goes into, there's a lot of literature on this. I mentioned some names. I'm not an expert on these extensions, so I might have forgotten some relevant things. Okay, so these are some applications, but now I'll go in the proof of the two main statements. So the first one was, if we have a E, a uniform rectifiable set, we have a function from E to R in the Sobolev space, then we want to prove this bound. And the proof will go through this good lambda inequality. So for any alpha larger than 1, and then which is close to 1 still, there is an epsilon such that for each lambda, we have this set, and this is the but set in a sense that here we see that the square function is large and the maximal function, so the gradient is small, and so here we want the opposite. But this lemma says that this set, which is the but set, doesn't take too much space, okay? And so let's see how we prove the theorem using this good lambda inequality. So of course, we start with the LP norm of the square function. We write this layer cake decomposition. We do a change of variable, nothing much from here. But now here we have this alpha lambda, which appears here. So we split this set into two. So this part and this part. So these are like sort of complementary. One is where the maximal function of the gradient is small, and the other where the maximal function of the gradient is large. And now what do we see? Okay, so this set, because of our lemma, should I go back? Do I? Okay, sorry. Okay, sorry. Right, so I was saying that, so we got here, we split this set into these two sets, and this is exactly the set we have control of. So now, if we bound this integral with this term here, now this becomes simply the LP norm of the square function by this layer cake decomposition, and because we have we were multiplied by a small constant there, we can hide it behind. Okay, and so we have the LP norm of the square function is bounded by this, and this of course is just the LP norm of the maximal function, which is bounded in LP, and we obtain the theorem. So I say, okay, this is very easy. So then the sort of core of the things happen in proving the lemma. And how do we prove the lemma? So this is what we want to prove. I'll just rewrite it here. Okay, and what do we do? So we take E naught to be the set where the maximal square function of the gradient is small, and this is okay. Now, if E naught is very small, then of course this is a subset of E naught. So then we are done. So we can suppose that E naught is large. Okay. Then on E naught, because of sort of the property of the high wash upper gradient, we have this fact. And so because here Gx and Gy are somehow the high-wash upper gradient, and we know the maximal square function is small, then they're also small. So we get that f on E naught is an epsilon lambda Lipschitz function up to constants. Okay, and this happens on a large set. Okay, so then I mentioned before that David and Sam proved that on uniform rectifiable sets, if you have a Lipschitz function, you have that this with also the measure on the set is a Carlson measure. So essentially, we get that this quantity is small. So f is really well approximated by affine functions. Okay, and then we transfer. So now f. Oh, sorry, I forgot to say what capital F is. Capital F is. No, I said it. I think capital F is the extension of f on the whole E. Okay, so now Lipschitz extension. Yes, yes, yes. And so now we transfer these good estimates that we have from capital F to F. Okay, so then we obtain this. And so this saying that because all this was done on a set with large measure, we end up with having that the square function of F is small on a large piece of our set. Okay, and then of course, this lies in the complement of this large set, and therefore we can conclude that this bad set doesn't take too much mass. Okay, this is, of course, they're like, I'm hiding lots of things and I'm lying, but this is the idea. Okay, so now this was the proof of the first theorem. Now I prove the second theorem. Okay, so we said that if you have a set, a uniform rectifiable set, and F is Lipschitz on E, then we have this bound. Okay, again, we go through a good lambda inequality, which says that for any k, but the point is that in this case, the bad set, of course, the role of the gradient, of the high-wash gradient, and the role, oh, this is the tangential gradient, sorry, and the role of the maximal of the square function are swapped. Okay, so if we can prove this, then we can prove the theorem simply by what we did, similar arguments that we had before. So now let us see how we prove this. So we take this set, where the tangential gradient is large, okay, with respect to lambda, and we split it up into maximal cubes. So if this is the set where this happens, then we construct all these maximal cube, which I draw very neatly. Okay, so suppose that now one of these is one of our maximal cube R. Then because of this maximality and because of definition, if AR is the best approximating affine function at the level of this cube of F, then the gradient of AR will be roughly lambda. Okay, so this will play a role later. And so then what do we do? Now we run a stopping time argument on each of these maximal cubes, which have 4 conditions. But the sort of most important one is the following. So we run a stopping time argument and we stop when we meet a cube whose, so that the best approximating affine function of our function f has gradient that is too large with respect to the gradient of the maximal cube R, okay? So this is what it is saying. And so in this case, we put Q in bad and we stop. Okay, and now alpha node is some constant that's close to K, but okay. Then the sort of main effort in the whole paper is to sort of prove this packing condition for this bad family, okay, which I won't go into the proof of this. But now suppose that we have this packing condition, and okay, so now recall that we want to sort of estimate the measure of this set. Suppose now T is another maximal cube in the same sense as before, but now of this set where like the gradient is large. Okay, then, okay, so let's see this computation. AT again is the affine function which best approximate my function at the level of T, and then the gradient is larger than KL because of definitions essentially. Now K, I said, is roughly alpha 0, and lambda, I said before, the gradient of the maximal cube R is roughly equal to lambda. So we can bound this, and therefore any maximal cube in here is contained in the bad family that we have this bound for, okay? And so, of course, this is contained in this set, and then we divide it up into this maximal cube, and each of these maximal cube is contained in a bad cube of the family B, which I defined before. Now we have a packing condition, and so we can see that this doesn't take too much mass, and essentially this is what the good lambda inequality says. Okay, and okay, so maybe this was a bit fast, but I hope you got the gist. Okay, so this proved the second theorem, and now maybe I have a few minutes to mention some possible further questions. So one, it would be nice to obtain this similar Dorronsoro type theorem, but with a different square function. And the square function I have in mind was, Alabert, Matteo, and Federer proved an equivalent Dorronsoro in RD with the square function that looks like this. Okay, so this would like, okay. And then one could define a gamma f, like in our case, with that Alabert, Matteo, and Federer square function, plus of course we need something that picks up the geometry, but here one could put the center of mass of the set. And in this case, it would be interesting because this square function would not have a linear structure to it. So it could be interesting for people that study differentiation in matrix space. And also would be like possible question is like if converse statements hold. So if now we show that if you have good geometry, then we have some quantitative approximation of Lipschitz function is the reverse, some form of reverse statement hold. And of course, I'm done. Thanks.